Now, something we've already discussed to some extent, I want to continue discussing. We're still on our partial fraction expansions, and how do you find those expansions? I want to look a little bit more depth on this special case here, and that is when our function, f of s, which is represented by a division of two polynomials. There's a numerator polynomial here called n, and then the denominator polynomial, believe it or not, is called d. So we have f of s is equal to n of s divided by d of s. And I'm going to write it in this form. The numerator remains n of s, but the denominator looks like this product. It looks like a big pi, a capital pi. I goes from 1 to n of s plus ai. Okay, now, first of all, you may not be familiar with this notation right here, this pi notation. So let me explain that to you. If we write down the pi, or the product, I goes from 1 to n of s plus ai, what we mean that when we write that is that's equal to s plus a1 times s plus a2 times, that's a2 there, times, keep on going, all the way till s plus an. So it means something like the summation notation, the sigma notation for doing sums, except this represents a product. So this symbol here means s plus a1 times s plus a2 times s plus a3, and so on, all the way out to s plus an. So that's what this notation right in here means. So here we have f of s is equal to n of s divided by this. And to write it as a partial fraction expansion, we want to write it as a sum that looks like this. So we want to write this in a form that looks like this. So how do we do that? Well, first notice that this summation notation, which you should be familiar with, can be written as, what this means is a1 divided by s plus a1 plus a2 divided by s plus a2 plus dot 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 plus a sub n divided by s plus a sub n. So the way we find each coefficient here is we do as follows. We want to find the coefficient a sub I for the would be the numerator term when s plus a sub I is in the denominator. We take our function f of s, we multiply it by s plus a sub I, and then we evaluate the whole expression at s equal negative a sub I. Okay, so we evaluate it at this point right in here, s equal to negative a sub I. So let's look at an example like one we've already discussed. Let's suppose that f of s looks like this. F of s is equal to s plus 3, so that's n of s, divided by s cubed plus 7s squared plus 10s. Okay, now we can factor this denominator as shown right here. So this is equal to this in the denominator. So here's our d sub s. We want to write it in this form. We want to write it like a1 over s plus a2 over s plus 2 plus a sub 3 over s plus 5. So we say, using our formula, we evaluate it at the a1 term by taking s plus a1. Notice that a1 is equal to 0 here. S plus a1 times f of s, and evaluate it at s equal negative a sub 1. And so s plus a1 is just, s plus a1 is just equal to s. So this becomes s times f of s evaluated at s equals 0. So when we do that, multiply this whole thing here by s, it becomes this expression right here multiplied by s becomes s plus 3 divided by s plus 2 times s plus 5. Okay, you see that, don't you? S times this expression right here times s. The s's will cancel and leave you with s plus 3 divided by s plus 2 times s plus 5. We want to evaluate that at s equals 0. We put in s equals 0. We get 3 divided by 10, or 0.3. Similarly, we can solve for s plus a2. Okay, that's equal to s plus 2. That's what a2 is right here. S plus a2 is s plus 2 times f of s evaluated at s equal negative 2. Okay, when we do that, we get this expression, and that's equal to negative 1 over 6, and we can solve for a sub 3 to be negative 2 over 15. So this is an example that we have done previously, and but this is a more general representation of how we solve for the partial fraction expansion when when we factor the denominator polynomial and it has distinct real roots. Okay, so until next time.